Okay, so remember, left side has to equal the right. So who thinks they got like the answer for those 3 boxes there? Yeah, go ahead.
0, -1, beta.
Love it. 0, -1, and then this is called beta, and the symbol for beta is either this B with the long tail, or you can put an E. If you're gonna put the B in formative, just put like literally the letter B. But understand, like it's not boron. It's this is a high energy electron. 0 plus 99, that would equal 99. That's why that would work. And 44 minus 1 would equal 43. So again, numbers have to equal each other. And again, beta decay. All right, who thinks they got this one? Yeah, go ahead.
So 4 is 32, 5 is 16, 6 is S4, right?
S, yeah, good, perfect. So ask yourself, if you're confused on how you got there, ask yourself 0 plus what would equal 32? That would have to be 32. And then -1 plus what would equal 15, and that would have to be 16. Then go on the periodic table, find the, this is the atomic number, smaller number is the atomic number, it tells you the element you're working with. Find the atomic number of 16, and that would go with sulfur. Okay, last one. This one's a little more going on here. Thinks they could get this one. Okay, go ahead. What did you say at the time? AT, yeah. Perfect. So talking through it, getting 4 and 2 here. So 208 plus what would equal 212? It would have to be 4. And then 85 plus what would equal 87? And that would have to be 2. Okay? So then once you've established that this is 4 and 2, then look on the periodic table, find the atomic number of 2, and that goes with helium. Remember, this is what kind of decay is this? He is a what? Alpha, right? So alpha decay goes with helium. Okay? And then AT, you would look up 85, atomic number 85, and that would go with AT. Okay? So really not too bad compared to like other things we've, especially compared to like half-life. Okay, so getting your notes out. So make sure that these are, so I gave you the answer, the first 10 problems in the formative. So everybody got these filled in? Okay. There's few things more frustrating than going around and looking at your formative and you literally don't have the warm-up filled in. It's like, if I can't get you to do the warm-up and I'm giving you the answers, how in the world am I ever going to get you to do like problems by yourself, All right. I'll get off my soapbox. Okay, so getting your notes out, find the fission fusion. It's the last bit of notes in the packet. And you're getting yourself to this slide. So, finding this slide, fission fusion. Go around and make sure we're all there. Remember, we're going to come back to the ion and atomic spectra on Friday. This first slide here. Remember, you can pull up the slide deck on your computer if you're having a hard time seeing it. Or if I'm going a little too fast, it's kind of a good general advice. Okay, so nuclear fission. Nuclear fission. Here's the idea. If you have a really large atom, like say uranium-235, pretty big atom. If you were to hit uranium-235 with a high-energy neutron, this will cause a nuclear fission reaction. Now, what pop culture, what kind of famous movie recently was in theaters that has the nuclear fission reaction? Yeah. Oppenheimer. So yeah. So everyone's sitting straight. Yeah. Anyways, Barbenheimer. Anyways, so yeah, this is the actual chemistry or nuclear physics behind it. You take a neutron, a high energy neutron. If you hit the nucleus of this uranium-235 atom, you can split this atom into two lighter atoms. But when you split an atom, you're going to release a ton of energy. So that energy can then be used for a lot of things, right? It could be, in the case of Oppenheimer, it could be used for a nuclear weapon. In the case of a nuclear reactor, it can be used to, power the lights or something. Now then, once you do this reaction, you'll create these lighter elements, but you also are then going to create more neutrons. And so then this neutron here can then react with these, the lighter elements from the first fission reaction, and along with other uranium-235 atoms. And so in other words, this becomes like a snowball effect, where as these neutrons hit these lighter elements, they keep releasing energy. And so, like a snowball rolling down the hill, the faster a snowball what's the best way to say it? The faster, the bigger a snowball gets, the faster it gets bigger. Say that again, if nothing else for myself. The bigger a snowball gets, the faster it gets bigger. In other words, exponential growth. That's what happens in a fission reaction. As you keep splitting these atoms and releasing energy and releasing more and more neutrons, you are then, so you got another slide to write down. So a lot of people are staring absentmindedly. You got blanks to write down? Anyways, as these neutrons are hitting these elements, you keep releasing more and more energy, and there you go. And again, that energy can be used for a weapon, or it can be used to, like, say, power, a power plant, whatever it might be. If you're wondering where my rollerblade went,
You got discontinued, right? Why?
Who snitched?
No,
No, it's not like that. It's just.
Who found out?
No.
It's not safe for me or for you.
It's so safe.
And it violates trust.
It makes my learning experience so much better.
I would like to think so.
And it's so
You had the picture battles.
The Fission is there an alternative for us? Dude, he's never used this really full body. Ice floor.
Okay, all right. Moving on. So, getting to like the reactions and stuff. You need to be able to identify which of these to be a nuclear fission reaction or fusion. Well, we'll talk about fusion in a minute, but looking here, so everybody focused up here, phone should be put up. All right, which one of these would be a nuclear fission reaction, and how would you know? I haven't explained this to you yet, but like, just thinking about what a fission reaction would be, how would you know? Put your phone up, please. Have it in your hand. I can see it. What are we doing here? All right, yeah. All the way back. Go ahead. This one?
Yeah.
Yeah.
Yeah, it is.
Huh? Now, how'd you know?
Because it like repeats. Like it'll keep going.
Yeah. So another way of saying that is like you have this bigger atom. It got split into two smaller ones, and there's one more detail. Bigger atom to two smaller ones, but then another detail. Think about the snowball effect I was talking about. Yeah, go ahead. You see more neutrons. Yeah, you're creating more neutrons there. Okay. What would this top one be? Think back to last class. What would you call that? Seen something like that before. Maybe the symbol's a little bit different. That'll be alpha, yeah. Right, okay. Now, what about this one? Alpha, yeah. This is actually the first time I think I've shown you one where they literally use the alpha symbol. But, anyways. Yeah. So, yeah, it would be C. So, yeah, because you get two smaller elements and because you have more neutrons produced than what you started with. Okay. So go ahead and make sure you mark C. And I think it's important to kind of some way for you to remember why. Some way to remember why it is a union. You don't have to write this whole thing down word for word, but you know, maybe you could say like bigger, like two smaller, like multiple smaller, and then more neutrons. Could be kind of the bits of kind of notes you could jot down. Stick with me here. Stick with the notes.
What is the third one?
This one, more neutrons. My handwriting is especially bad. This one. What's up? Yeah. Oh, yeah, good point. Hey, this N stands for neutrons, if you're confused by that. The N is for neutrons. Good question. Which does bring up a good point. The reason why this would be the symbol for a neutron is because this is the mass number. Neutrons have a mass of 1, and they're neutral, right? They don't have a charge. So that's why there's a 0 there. All right, keeping it moving, nuclear fusion. So if fission was to break apart, fusion, if you're going to fuse two things together, that's going to be the opposite. So you're going to combine elements together. Now, nuclear fusion is more of like a futuristic kind of energy source. It's not something, it's something we can technically do now, but we can't do it on like a scale or like in a cost-effective way yet.
Yeah, I remember reading last year.
Yeah, no, there's so many labs working on nuclear fusion. Like it's definitely like it's not like a time machine. It's not something that's like super far off. It's like conceivably in my lifetime they could develop it and make it at scale. But here let's go through like a reaction here. So like here they have what they call deuterium. So deuterium, this would be hydrogen with a mass of 2, and it's going to fuse with tritium, which is a hydrogen with 2 neutrons. Don't need to memorize that, but basically 2 hydrogen atoms you're going to fuse together, and in the process you form helium, right? You add 2 protons. Once you get 2 protons, you're now helium, and then you're going to release some neutrons, and then because this helium is more stable than these 2 individual atoms are separately, you will release a bunch of energy. Okay? But to get them to that point, you have to invest a lot of energy to get out even more energy. That's why it's so cool. It's like when you see like you're like, geez, I wish I could invest in like some startup company that can make a lot of money, but I don't have money to invest with right now. It's a similar idea where it's like you got to be able to invest a lot of energy initially to get out even more. Difference in mass between the reactants and products is the amount of energy released or absorbed. This is true. It's not super important that you have that memorized or are walking around with it. I just want you to know the basic definition of a fusion reaction. Opposite of fission, bringing 2 smaller elements together, making a slightly bigger element, and then releasing more energy. Okay, so then, and then the other thing is being able to identify whether a fission or a fusion reaction has happened, and then predicting the products. So this is pretty similar to like what we saw with nuclear decay. Similar idea, left side has to equal the right side. So here, if I want to predict these products, first off, fission or fusion?
Fusion.
Good. heard a little bit of both. It's going to be fusion. Now it's fusion because you're taking, it's fusion if you have more reactants. Like more than one reactant. Fission, you're just going to have one reactant. So fission, if you have one reactant, like for example 7 would be fission because you start with one reactant. Okay? And then you'll end up making more products. Fusion, you'll have more reactants, and then you make fewer products. Now, then we got to predict these products that come from there. So, who thinks they could tell me how would you predict this? Yeah, you got it.
You add 56 plus 59, and
Yep.
then do 26 plus 28, and then
Yeah.
so then it's 105 and then 54, and then I think in order to find what element it is, I think that you search for like 54, which is XC.
XC. There it is. Love it. Okay. So again, add these mass numbers, you get 105. Add the atomic numbers, you get 54. Okay. All right. Now then, a fission reaction. We're going to take this element and break it apart into smaller ones. What would be my my products here? Or my product here? Any thoughts? What am I producing? How would I find that out? Remember, left side equals right side. Okay, go ahead. Yep. Yeah. Good. Okay, so yeah, add up your atomic numbers. So that adds up to 56. 42 plus 14 is 56. Subtract that from the atomic number that you start with over in the left side. 105 minus 56 is 49. Mathletes? You know what I'm saying? Okay, so 49, that's your atomic number. Because again, go repeat it back to yourself. 49 plus 14 plus 42, that equals 105. Okay? All right. So then, similar thing, got to get the 262 on the right side. So 96 plus 28 is a number that is 130. That is definitely not 138. 134? 124 is my second guess. 124 is what you get if you add 96 and 28. Then if we subtract 262, or subtract 124 from 262, we get 138. That is correct. That's correct, young man.
That is correct.
Okay, so 138, that's your mass number. All right, now then we got to find the symbol that goes there. So what's that? What symbol? You got it? IN? You got it. This guy's back there should be teaching the class. Okay, last one. So fission or fusion? Fission, yeah. Start with, you got one reactant there. Make sure we get phones up for me. You know, back in my day, you had the flip phones and you could feel the keys. This is gonna blow your mind. So you could like feel like the keys. Like I could text without looking. I quite literally could have a hoodie, and I had memorized where my best friend was in my contacts. I could send him as long of a text as I want, and just be looking you right in the eyes.
That's crazy.
Yeah. Everybody's gonna go by flip phones now. But you can't. Yeah. But you can't do that anymore because iPhones you gotta look at.
Remember, I get gone one down and by accidentally text that one.
Yeah. You send some love text to your mom. I don't know. See. Okay. Anyways, last one here. So left side's got to equal the right side. So 265 is your mass number. So 16 plus 9 is 25. Okay? So then 265 minus 25 is 240. 240. Okay? Alright. Then 8 plus 4 is what? 12. 108 minus 12 is 96. Okay.
And then tax CM, which is
That is
CM.
CM. Sure enough. So, you know, it's you could almost call it fun. You know, I don't know. If it not like best weekend ever fun, but like, you know, it'd be like a below average weekend. You know, Saturday morning. Okay. I'm gonna go around and make sure we all are conscious and have written this down. There. There. Okay. What do you do with them? You just I mean, you're not making bombs.
Not like these ones, but like in general.
I mean, like, yeah, people who are like nuclear chemists or nuclear physics, yeah, the work they do is based like very, very loosely on these equations, and then you go from there with like the work and stuff. Yeah. Anyways, yeah.
So, like, could we actually, like, legally make bombs?
No, we can't legally make like. What world would that like? Could you legally make bombs?
I don't know, the military.
What are we talking about right now? I can't even remember rollerblades. What are we doing? Okay. Drop beats, not bombs. But we do have to talk about bombs. So, atomic bombs, again, that comes from a fission reaction. Okay? Now, there's actually, if you're like, well, hey, could fusion be used as a weapon? And the answer is yes. Yeah, that would be the hydrogen bomb. Okay. This is he read the USA Today article. Like, my guy's well read. No, he's just well read. He's well educated.
We good though.
We're yeah, good question. Hydrogen bombs are more powerful. So, that's a fact, right? Regardless of your opinions on bombs and stuff like that, it is important that you kind of have a basic understanding of like what they are, where they're coming from, and all that. And that's kind of really what I want you to get. Maybe this slide here might be kind of the biggest take home from this lesson. All right, guys, back there, almost done. Keep it together. Got one more slide. We good writing on this slide? All right, cool. Yeah, one more slide. So, another application of fusion is the sun. If you ever wondered, like, how does the sun make its energy? Nuclear fusion. Yeah. So in the sun is not just a big. The sun is a big fusion reactor that creates energy. It doesn't create it's sure. Like, come on.
Let's be honest. Is it not just blow up like
I suppose, yeah. I don't know. You're kind of on my pay grade when it's like, when is the sun gonna explode? You know, I don't know.
Oh, you know.
I was looking about that.
You were like, no, big lots. I was wondering why you look so tired. Just like, like, what's the point of getting this history homework done? Sun could blow up at any moment. You know, actually, that's my best one.
Actually, no. When the sun is also falling off,
So what?
Yeah. Maybe you got a long time for the sun.
What's the point of it?
All right. Yeah, so again, Fusion is a futuristic energy source, guys. Like 10 seconds. Sun is a futuristic energy source. The fusion of hydrogen will then create helium. This is also how all the elements were made. Like, you think back to the beginning of the universe. Notice how hydrogen, two hydrogens combine to make helium, which is a heavier element. So these heavier elements are made from the fusion reactions that are happening in the different suns and stars in the universe, which I think is kind of cool. All right, so you got a formative. Go ahead and finish up those problems in there. I'll be going around if you got questions. Cool.